Okay, so today we will talk about the various reaction types and mechanisms. Now, what I intend to do in this class, I will discuss about various types, as you will see. Just a second. Yes. So, first there will be these various classifications. First we will talk about fast and then slow reactions. One classification. Next will be whether the outcome of the reaction is a two-body reaction, how many products you see as a result of the outcome. Okay, you see 2 nuclei or 3 nuclei. Then we will talk about a little bit different category of heavy ion reactions. Now, in case the transfer is very large during a nuclear reaction, a large number of nuclei are transferred, then we will have a massive transfer reaction, which is a deep inelastic collision type reaction. And finally, we will talk about the classification in terms of incident energy. There we will talk about sub-Coulomb energy reaction, or basically the thermonuclear reaction. Then we will talk about the classical nuclear physics reactions. They are basically reactions above Coulomb barrier and below the Fermi energy. And then we will talk about intermediate energy nuclear reactions. That is reactions where the energy is above the Fermi energy. Okay, so this is basically what I will be going to talk about in this class. So 1, 2, 3, 4 and then this 5. Also, I will talk about the various types of these fast reactions, direct reactions, various categories as well. Fine. So, let's start. Now, if we categorize in terms of time scale. So, if you do the categorization in terms of time scale, then reaction time scale. Now, let me write down the time scale then. So T is equal to d by v, distance by speed. Again I can write this as d by non-relativistic expression for velocity. If I consider, then this will be my expression. Again this is equal to d by c into twice E by mc square. Okay, just a second. Okay, so let us continue. Now, so as I was saying, reactions, as I have told you, can be broadly classified depending on the time scale of interaction or by the number of products they produce in the final state. Now, there are a number of reactions that occur in the time scale which is required for the projectile to traverse, you see, the nuclear dimension. So if this is your nucleus, right, then the time required for one projectile, suppose some projectile is entering from here and the time it required to cross. Let us first estimate this time scale, and this is what I am doing here. So in this expression here, d is the nuclear dimension, and E is the energy of projectile, and mc square is the mass in MeV, right? Of course, C is the velocity of light. Now let us consider a proton. Suppose a proton, consider, let us, okay. Now for the proton, the mass will be 931.8 MeV, right? So, and if you use the nuclear dimension D, if this is the mass, just a second, yes, if this is the mass and if D is approximately 1 Fermi meter, you use this, then from here you will see that the time scale you get is 3.3 into 10 to the power minus 22 seconds. See, so this is basically the typical time scale of a nuclear reaction if the interaction involves only few interactions. That means when the proton enters here, if the proton is entering and there is very hardly few interaction of this proton with the other nucleons inside the nucleus, then it will not interact that much. Instead, it will just pass up directly, and this is the time scale. So remember, the time scale is roughly 10 to the power minus 22 seconds. Okay. Yes. So this is the time scale. Next. Okay. Now, so this is basically we are talking about right now direct reaction. So direct reaction, the time scale is approximately 10 to the power minus 22 seconds. Now you see, this is because there are very few interactions of the projectile inside the nucleus. Okay. Now, however, much slower interactions are also observed. So basically, if there are large number of interactions, so this is the nucleus, the proton enters and there is a large number of interactions of this proton, then the time scale will be much larger. And normally these larger time scales are of the order of 10 to the power minus 14 seconds, and sometimes, no, most of the time this also involves electromagnetic emissions as well. Okay, so this was direct reaction and this is basically your compound nuclear reaction. Now, so this classification of direct reaction and compound nuclear reaction, here you see, so this is the classification in terms of time scale, and this fast is the direct reaction and the slow one is the compound nuclear reaction. Now let me talk about the two body and three body.
Electromagnetic interaction ki bolna?
What I am saying is that during the compound nuclear reactions, after de-excitation, there is electromagnetic emissions as well. Gamma rays, say for example, are emitted when the nucleus de-excites from its excited state. Okay. Now, so let us talk about the case of, again, this time I am talking about direct reactions here. Now, direct reaction can be further classified on the basis of final states. So, number of final states. If there is two body final state or there is three body final state. Okay. Now, they show widely different characteristics in terms of energy spectra and angular momentum, these two scenarios. Now these type of reactions, transfer reactions, you see, that produce two body states have discrete energy states. So two body states, they have discrete energy states. Okay, whereas breakup reactions, which is basically a three body reaction, have so basically continuous energy spectra. This classification is important, okay? You must remember this. So we have talked about two classifications. Number one, in terms of time scale. Next, number of final states. Fine. Anyone having any question? This is very simple basically. Now let me talk about the heavy ion reaction. Okay. So basically you see, the case for heavy ion reaction is quite different compared to the light ions. So here we are mainly talking about light ions, right? However, this one is a heavy ion reaction. Now the question is, how is this different? You see, in the case of heavy ion reaction, greater amount of angular momentum can be transferred. Okay, now this is because you see the angular momentum is proportional to the reduced mass of the two nuclei. Remember, L is equal to mu Vr. Okay, so this is the scenario. So now let me talk about the classification in terms of incident energy. So just a second, where is, yeah, here. So now classification in terms of incident energy. Now usually you see for reactions with energies below the Coulomb barrier, let me write this in a separate page. So classification in terms of incident energy, right? So when the energy is below, again, which energy? The incident energy is below the Coulomb barrier. Okay, then we have what is known as sub Coulomb energy reactions. Okay, now such reactions basically we observe are related to thermonuclear reactions in stars. This we have covered in our previous classes, remember? Okay, now next is reactions above Coulomb barrier but below Fermi energy, which is around 33 MeV per nucleon. Now this is the region of classical nuclear physics. Most of the time we talk about these nuclear reactions, right? Now energies which are above incident energy, when the incident energy is above your Fermi energy, then we have basically the intermediate energy reactions. Now they are very different in nature. In our lectures we will not cover this one. Basically this thing, where is the, just a second. Oh, yes. basically this we have covered in our nuclear astrophysics class, and this is what we will cover mostly in this set of lectures. And this I am not going to cover, this is quite advanced, the intermediate energy reactions. Fine. Okay, so now we have covered most of this stuff, right? Good. So before I proceed, let me ask if you have any questions. Okay, so now let me talk about the deep inelastic collision, this one. Okay, fine. Now you see, in the case when there is massive transfer, that is large number of nucleons, large number of nucleons are transferred between the projectile and the target, or basically we have in this case massive transfer reactions, and so we have as a result large Q is observed. Q value is observed in this case. Fine. So these are deep inelastic collisions. Okay. So we have talked about deep inelastic collisions or massive transfer reactions and other parts as well. So let me now again come back to number of final states produced. Case this one. So let us talk about it in more details. Fine. Now, as we have already talked about, on the basis of time scale, nuclear reactions can be broadly classified into direct reaction and compound nuclear reactions. Now, direct reactions can result in two-body final states as well as three-body final states, right? Now again, this two-body final state again can be of two types. This one can be of two types. In one type, the initial pair of nuclei P and T, projectile and target, they do not change. To different set of nuclei that is ejectile and residue. If such a case happens, then we have got basically scattering. Now again, scattering can be of two types. So this is the scattering case. Again, scattering can be of two types: elastic scattering as well as inelastic scattering, right? Now, of course, in the case of elastic scattering, the initial pair of nuclei remain the same after the nuclei interact. Only the kinetic energy and the direction of motion are altered. So in this case, only kinetic energy and direction changes.
Sir, kinetic energy ও চেঞ্জ হবে?
তোমার কি মনে হয়?
ইলাস্টিক স্ক্যাটারিং এ তো এনার্জি আগে একদিন পড়াচ্ছিলেন মনে হয়, শুধু বললেন ডিরেকশনটা চেঞ্জ হবে।
বলো, কে বলবে? Tell me whether kinetic energy changes or the direction changes. Of course, there is no issue in the fact that scattering means that direction will change. Of course, in the case of scattering, the direction will change.
ইলাস্টিক স্ক্যাটারিং শুধু ডিরেকশনই তো চেঞ্জ হয়, কাইনেটিক এনার্জি চেঞ্জ হয় না।
Now tell me, have I talked about excitation of the nuclei?
No.
Have I talked about the excitation of nuclei? So basically we are talking about this reaction, projectile plus target forming projectile plus target. Here on another possibility, which is the reaction, eta hocche this channel is scattering, so projectile plus target forming projectile plus target. Okay, so did I talk about excitation or not? Have I talked about it? Now in the case of inelastic scattering, what can happen is, in this case, sometimes the kinetic energy doesn't change. What does this mean? It is coming, then just only the direction is changed in this case. Now let me talk about the inelastic scattering over here. See here, what I haven't talked about the fact that the total kinetic energy changes. Total kinetic energy remains same. Total kinetic energy before and after the collision in the case of elastic scattering. However, the total kinetic energy can change or not. Again, tell me.
No, sir.
Tell me. I am saying that in the case of elastic scattering, the total kinetic energy, it remains the same. I am not talking about the fact that the kinetic energy differs. Total kinetic energy is conserved. However, one can have slightly different kinetic energy, but the total kinetic energy remains the same. বুঝেছো? Now, okay, now in the case of inelastic scattering, in this case you see one or both the nuclei get excited. Here excitation enters the picture. So from ground state there is an excitation to higher energy state, and this excitation is due to interaction. Okay, so this is the feature of inelastic scattering. Now you see, in two-body reactions, apart from scattering, there can be rearrangement or transfer reactions. This one, transfer reactions, right? Now what happens in the case of transfer reaction? In the case of, you see, transfer reactions, so if this is a projectile and this is a target, then what happens is a part of the projectile, it gets transferred something. In fact, sometimes a part of the target can also be transferred to the projectile. So there is transfer of nuclei between the projectile and the target. Okay. Now, if a part of the projectile gets transferred, so if we have got the former case, this one, a part of the projectile gets transferred to the target, then we have this reaction is known as stripping reaction. Since the projectile is stripped of nuclei. Again, on the other hand, if a projectile picks up, in this case, there is stripping of the target, stripping of nuclei from the target, but we give importance to projectile. So, if a projectile picks up, so in this case, you see, there was stripping of a nucleon from the projectile itself, and on the other hand, if the projectile picks up one nucleon from the target itself, then this is known as pickup reaction. Okay, now in either elastic or inelastic scattering and transfer reaction, the Q values are either 0 or very small. So, they are sometimes known as quasi-elastic reactions. Quasi-elastic reactions, that is like elastic reactions. And why? Because of small Q value. So basically, this is for elastic scattering, then inelastic and transfer reaction. These three are collectively sometimes known as quasi-elastic reactions. Okay. If someone wants to ask something, please ask. Fine. So we have talked about quasi-elastic reactions. So as I was saying, sometimes previously I talked about the deep inelastic collisions. Yes. Where there is massive transfer. Massive transfer of number of nucleons. And as a result, we have large Q value. Okay. Now, again let us talk about direct reaction. And so previously we talked about nuclear reaction, direct reaction, two body final states. We talked about this. Now we will talk about the three body final states. Okay. So three body reactions such as three body reactions such as breakup or knockout. Knockout reactions. They also form part of the direct reaction. Now, in a breakup reaction over here, what happens is the projectile fragments into its constituents. So here projectile fragments into its constituents in the field of course, Target nucleus. Who else is there to influence it? Only because of this fact itself the reaction is happening, right? Now these reactions, however, become favorable when the projectile nucleus has a loose bound structure. So favorable when projectile nucleus has loose bound structure. You understand this thing? If the projectile has a loose structure, then in this case it can of course break into two different parts. Okay, so now stable loosely bound nuclei and most of neutron rich radioactive nuclei are the various candidates for such type of reactions. So basically stable loosely bound nuclei and most of neutron rich, of course they are radioactive nuclei, they are the ones where such type of projectile breakup. When I am saying breakup, remember this is basically projectile breakup reaction. Okay. Now on the other hand, this one knockout, a light nucleus or nucleon knockout represents a constituent. Let me write down in a separate page. So okay, knockout reaction. So basically what happens is that here a constituent of the target producing a three body final state happens. So basically here a light nucleus or nucleon knocks out just knockouts. Yes, this represent a constituent of the target producing a three body final state, right? So in this case we have a knockout or target breakup. So knockout means basically also target breakup reaction. That was projectile breakup and this is basically target breakup reaction. Any questions till now? If no, then let me talk about. Yes?
নকআউটের ইয়েটা আরেকবার বলুন।
So let me again draw. You see, in the case of projectile breakup, the projectile is loosely bound and it has basically two different parts, say small a and small b, and when this happens, this enters the field of the target nucleus, then what happens is that one of this just goes away in a separate path and another one reacts with the target. Okay, so let me talk about a different case of knockout reaction. So basically if we have again target and we have got a projectile small a, and when it enters the nucleus, as a result of the interaction enters the field of the target, then there is some part of the nucleus, say small b, it interacts with it, and then this part A and B are produced, and then we have got a residual nucleus, so an ejectile. So previous, let me write it down so you understand. So this comes and knocks it, this part. Now B can be one nucleon or more than one nucleon as well. So as a result, we have got a new nucleus. This AB is formed, and another separate one which was target minus the B nucleus is formed. So this is your target breakup reaction. So this is target breakup reaction, and this is the projectile breakup reaction. We will now talk about the compound nuclear reaction. Fine. Now, this compound nuclear reaction is basically a two-body reaction. Where the final products are formed by decay of an intermediate nucleus, okay, which is again formed as a result of amalgamation of the projectile and target, and this is what is known as this amalgamation, Miller-Gallo. This is known as fusion reaction. Now you remember, a fusion leads to formation of an excited compound nucleus that mainly decays by emission of first light particles like neutron, proton, deuteron, others, and later on by electromagnetic emission. Now this emission of light particles is known as sometimes evaporation reaction. So let me first write this. So basically amalgamation. So final state, final products are formed by decay of an intermediate nucleus formed by fusion. Okay, and as a result we have excited compound nucleus which decays by emission of light particles like neutron, proton, deuteron, etc. And this is known as evaporation reaction, as if the light particles are getting evaporated. Remember, this evaporation reaction represents the major decay mode of the compound nucleus, and the emission of these light particles de-excites the nucleus. Suppose if it does not possess any more energy, then it decays by gamma emission. So first we have basically evaporation reactions, and later on we have, where is it? Just a second. So first we have evaporation reaction. So first we have evaporation reaction, then we have gamma emission. Now this gamma rays only decay between the low lying states of compound nucleus, and so this is the, you can get a signature of the structure. Now in this process sometimes statistical gamma rays can also be emitted which compete with the particle emissions. Here, this one, statistical gamma rays, they also compete with these particle emissions. The compound nucleus can decay by two massive, you see, the compound nucleus, there is another possibility, that is, it can also decay by massive two fragment emissions, and this is known as fusion fission reaction. Fusion fission reaction, and this is when we have there is decay by two massive fragment emissions. We have basically two massive fragment emissions, right? However, you see fission occurs mainly in the actinide region. In this case, that is Z is greater than 92. In some lighter nuclei, mainly asymmetric fission occurs. Okay, now let's continue to the last part. So what about the time scale? You see, the time scale is between your compound nuclear reaction time scale, and it is greater than your direct reaction time scale. That is, it is greater than your 10 to the power minus 22 seconds and lesser than 10 to the power minus 14 seconds. Did I write it correctly or wrong?
Correct, sir.
Tell me, students are sleeping or not? Or I have to check. ঠিক আছে তো? So my question is, what happens in this case? Right? What happens? So you see, in the case of direct reaction, this we talked about, the proton, say for example the initial projectile, it enters, and without much interaction, very few interactions after that, it exists now, right? And what happens in the case of compound nucleus? When the projectile enters, there are so many interactions that the history where it has entered, from the direction, how much energy the projectile came with, the entire history is lost. So there are large number of interactions, and here we have got very few interactions, right? So there will be a case which is in between. That means intermediate between the direct and compound nuclear reaction, and that reaction is known as pre-compound reaction. And what happens is that in this pre-compound reaction, you see, particles are emitted after few interactions, which is more than the number of interactions in direct reaction case and less than the number of interactions in compound nucleus, or basically here the number of interactions is much lower, and so the number of particles are emitted before the formation of compound nucleus. Understand? Now normally it is observed that pre-compound reactions we see when we have 10 MeV per nucleon energies, and they are sometimes associated with doorway states. Just know this name for the time being, doorway states. That is, states that may lead to either direct reaction or to compound nuclear reaction. So either direct reaction or compound nuclear reaction. So these are doorway states. Fine. So you see, we have covered lots of types. So we talked about the classification in terms of time scale, then direct reaction, number of final states, 2 body, 3 body. We talked about heavy ion reaction, then large number of nucleon transfer, right? We again talked about classification in terms of incident energy, thermonuclear reaction, classical nuclear physics reaction, intermediate reaction. Then again we talked about here, you see, the 2 body and 3 body final states. In the case of 2 body final states, we talked about, so here 2 body and 3 body final states, direct reaction mainly. We talked about scattering, then we talked about elastic scattering, we talked about inelastic scattering, and then we also talked about transfer reaction. And in the case of transfer reaction, before we talked about both stripping and pickup reactions. Then we talked about quasi-elastic reactions, right? Next we talked about projectile breakup and target breakup reactions. Here we talked about both of them, projectile breakup reaction and also target breakup reaction. This target breakup reaction is also known as knockout reaction. So target breakup reaction or your knockout reaction. And finally we talked about compound nuclear reaction, the various details. Okay, we talked about what is evaporation reactions, then fusion fission reactions, and then finally we talked about the pre-compound reactions. Good.
এটা স্যার কম্পাউন্ড নিউক্লিয়াস তৈরি হয়ে ডিকে করে ওই জিনিসটা, আর কম্পাউন্ড ইলাস্টিক স্ক্যাটারিং
So
যেটা ডিকে করে।
I have not talked about compound elastic scattering. Now what you are seeing over here in this figure, basically this shows a schematic stages, okay, various conceptual stages of a nuclear reaction. This is sometimes, this was after Weisskopf, he did that. So basically shows the conceptual stages of a nuclear reaction. Now you see incident particle comes before the field of the target nucleus. There can be elastic scattering, remember, and that elastic scattering is known as shape elastic scattering. However, there can be a possibility where the after the formation of the compound nucleus, it emits a particle which is of the same kind as the projectile, right, with the same energy that the projectile had. And what will you call it then? It behaves like an elastic scattering. However, this has happened after the formation of compound nucleus. So to distinguish it, we call it compound elastic scattering. Okay. And then we talked about the various possibilities of direct reaction. So this is the different channel. So I wanted to highlight the difference between shape elastic and compound elastic scattering. You see, what I am saying is that A plus A, it again forms A plus A. Now what has changed? Say kinetic energy somewhat is changed, just like in billiard board collision, and the direction is changed. So this is your shape elastic scattering. However, if this reaction proceeds through the formation of compound nucleus, then during the decay of compound nucleus has various possibilities of decay, right? However, during the possibility of the decay, what time is there, how much time it takes? around 10 to the power minus 14 seconds. However, if it is a sort of elastic scattering, the time is much lower, of the order of 10 to the power minus 22 seconds, right? So এই যে এতটা সময় লাগলো, it took so much time, and it again forms A plus A. So do you think the two processes are the same? No, they are different, because this is there in this case, that is in the case of compound elastic scattering, the angle of scattering will be different compared to that for the shape elastic scattering. Although they have the same energy, same sort of, what you can say, same species, but the scattering signature will be different, and this will be because of the compound nuclear reaction itself.